Okay, let's get started on this wet Friday. We are getting through. We're sort of like halfway through, I guess. What I've put up here is quite an important consequence from Bloch's theorem, and it's a bit related to what we had at the very start when we were looking at the reciprocal lattice and the free electron model. Okay, so this is important for when we are wanting to do so-called band count, electron counting to see whether bands are going to be filled or empty, and whether your material is going to be predicted to be a metal or semiconductor. So let's just look at what we've got here. Remember, we've got some solid, and our solid has the dimension LLL, okay? And inside our crystal, we have lots of little unit cells with lattice vector A, or lattice constant A. So these are all your little unit cells. And so this is our band structure in the reduced zone scheme. So what we want to know is how many electrons we can actually put in a given band. How many electrons can a band hold? So if we just consider one dimension, just say going along here, dimension 0 to L, then we know that the allowed K values will form a mesh with spacing 2 pi over L, okay, where L is the length of your crystal here. So the bigger the crystal, the more finely spacing these K points will be. These are the allowed K values, okay? But we also have the periodicity of the unit cell, okay, which is a smaller length than the actual crystal. Therefore, in reciprocal space, the unit cell in reciprocal space, your Brillouin zone is 2 pi on A. Okay, so to figure out how many states your band can hold, we need to divide 2 pi on A, the length here in reciprocal space, divided by 2 pi on L, that very fine mesh of K points. In that way, we can find out how many states, how many little K points all throughout here. And the bigger the crystal, the more finely your allowed K points, obviously. And the answer is N. Now, N is exactly equal to the number of unit cells in your crystal. So let's just pause there and digest that. So we have N unit cells in your crystal. The number of electronic states that can be in the band in the Brillouin zone, the first band, is equal to N. Okay? So this is important to understand that. Now we also know that each state, each electronic state can hold 2 electrons due to spin up and spin down. Okay, so the maximum number of electrons that a single band, if we just consider the first band here, is equal to 2n, okay, because you've got n states and you can put 2 electrons in each state. Okay. So that's important to remember. We'll do some examples of this a little bit later on, the electron counting. Okay, but now we want to, move on from last lecture where we are going to look at the nearly free electron model. So basically we're going to consider the electrons as if they're free electron waves, and they're going to be perturbed only very weakly by a periodic potential from the atoms in the solid. And this is a good approximation for some metals, and these metals are even given the name nearly free electron metals. So, for example, you might have sodium or aluminium, magnesium, potassium. Materials like that are nearly free electron metals. Okay, so what do we start off with? We start off with a Hamiltonian here, and this is the potential that we introduce. It's very weak. It's also periodic, as indicated by the potential at R in any given R is equal to that potential in the next or in any other unit cell. Okay? And as I said before, this is a good model for simple metals like sodium, potassium, aluminium, and so on. Okay, the matrix elements that you will form around the potential are given here. These are just the Fourier coefficients because you remember we can expand the potential V of R as a Fourier series due to the periodicity. Okay, and any plane wave state K can scatter into any other plane wave only if they are separated by a reciprocal lattice vector. Okay? Okay, so what we're going to do is use perturbation theory, and this has gone through very more detailed in the textbooks, so I'm putting here the key equations that are given there. So basically here, to the first order perturbation, it just gives an average potential in your unit cell. So that's just a constant value, and so we basically ignore that because it's just constant shifts up or down. And second order perturbation theory, we have this term here, which you'll probably know from your quantum mechanics, the basic form of it. But when we look at it, we can see that these are the energy eigenvalues at particular k vectors. There are some situations where these two become almost equal to each other, and in fact equal to each other. And when that occurs, this here becomes infinite, and this perturbation expansion is no longer makes sense. Now, so when do these two become equal to each other? It's when we have basically the wave vector k and k dash are separated by a g vector. And you know that that is when we are at the Brillouin zone boundaries. Okay? So whenever we are at the Brillouin zone boundaries, we have these two energy eigenvalues are the same. How can I show you that a bit more? I think the next slide, yep. Okay, the next slide you can see that more simply what is meant. Okay? So here, if we are at the Brillouin zone boundary here, this might be K, and these are just plus K and minus K. So K dash is minus K. You can see here that the energies are exactly the same, and they are separated by a G vector. Okay, so that's what we're talking about. Okay. So you know that we, also call these zone boundaries are also your Bragg scattering planes. Okay, so how to solve or how to describe that situation when you've got these two degenerate states? One uses degenerate perturbation theory, which you may have done in your quantum mechanics. So basically, we are going to deal with a situation where we have those two waves that have degenerate energy at the zone boundary. So we are now just looking at those states at the boundaries, okay? And from our matrix elements, we have, for a given k, energy is E0 of k, where 0 corresponds to the energy from the first Brillouin zone. That energy is just this energy here, okay? And for k dash, we have a similar energy here, and they are equal and separated just by a G vector from that previous diagram. We have the matrix elements, the scattering k to k dash, given by our potential here, and then the other way around This is the other part of the potential, scattering the other way. Now, we're going to write down the wave function at the zone boundary as psi equals alpha k, where k is just a plane wave, e to the I k dot x for one dimension. And we have k dash, again, equals k plus g, because we are only at the zone boundary. And we can get here the eigenvalue problem. And so what we're going to do is solve this and try and see how the energy eigenvalues are affected now by the presence of this potential here. Okay. So I might just slow it down a little bit and put it up here. So let's just think about what we've got. We've got our matrix. Well, first of all, we have, what is that? Yeah. K here. And two coefficients or eigenvectors, alpha and beta, equals to E alpha beta. So we're going to solve this the usual way, putting the energy over here. And over here we have V of G minus E so we find the determinant. And put that equal to 0. And so we end up with our expressions here, E of k minus E0 of k plus g minus E minus G complex conjugate equals to 0. And in this situation, we have the degeneracy at the zone boundary, so we can equate this k with k plus g. So at the zone boundary, E0 of k equals E0 k plus g. And so if we put this term just to be equal to this one here, we just get the square of those terms. Okay, and this is equal to just the magnitude of Vg squared. Okay, so taking the square root, we just get E is equal to E0 of k plus or minus V of g. So in the presence of a weak potential at the zone boundaries, we get the opening of a gap. So this kind of working shows you how we get the opening of the band gap at the zone boundaries, essentially. So, you know, we may have had this kind of situation here when in the absence of the potential, so it's pi on A minus pi on A, This is in K space. This is your energy. So what we have now is kind of at the zone boundary, we get two values of E. So if this was E0 here right in the middle, then we get a lower energy here, and then we get the plus energy. Here's another VG up here. So that the value of the gap is equal to 2 VG. Okay. I think that's kind of clear. Okay, so that's basically what we just did a little bit more briefly. And this is what I tried to sketch there. So in the nearly free electron model, when we introduce a weak perturbation potential, V of G, it opens up a band gap here where the value of the band gap is twice the magnitude of that potential. Remember before we also had defined the group velocity, and so that is equal to the gradient of the dispersion curve, energy versus K. So at these zone boundaries, we have the group velocity is 0. Also, you can see that the group velocity is 0 here at K equals 0. Okay, so that's the first thing. So, okay, we've looked at the energy. Now we can look a little bit at the corresponding wave functions. Okay, so what is this? Remember, we're still looking just at the wave functions at the zone boundaries. We have looked at their energy, and we have found how the band gap opens up. So now we want to look at the wave function. And, okay, in this diagram here, some potential has just been assumed. It doesn't enter into the working, but it's just drawn there, this kind of V of X, this weak potential. Okay? But remember from before, we had expressed our wave function as being equal to alpha ket or k vector, k state, plus beta other k state. So what you can do is go back into that secular equation that we just wrote down, and you can find that alpha will equal to plus or minus beta. That's kind of, I won't bother doing it. It's kind of straightforward. You can test for yourself. You put alpha equal to plus beta, go into the secular equation, and you'll find that it solves the equation. You put alpha equals to minus beta, and you also find that it satisfies the equation. So these are basically solutions. So you can write your wave function as being equal to 1 over square root 2. That's the normalizing factor, k plus or minus k dash corresponding to plus beta or minus beta. Okay, where what we mean is the k, this is in reciprocal space. In real space, it's just a plane wave. Okay, e to the I k dot r is k. And we're at the zone boundary, so for x, we just put in pi on a. And over here, for the negative case, the k dash, we just have this situation here. So basically, when we construct the plus wave function here, we get this situation, so this one plus this one. And when you kind of expand that exponential, you find that that's just proportional to cos. And analogously, for the minus we here going this state minus this state, or if you like this state minus this state, we get a sign function. Okay. So what does this mean? So it means at the zone boundary, we've got these two states which correspond to plane waves propagating in the opposite direction. Okay. Remember we said they were Bragg planes? This is all a little bit abstract, but I'm trying to tell you what it means. So we've got Bragg planes at our zone boundaries, and when we're thinking about electrons in the solids, at that situation, at the zone boundary, you can think of it as two plane waves propagating in opposite directions, and you know what that gives you, okay? It gives you a standing wave. Okay, so at the zone boundaries, we have standing waves. And they correspond to reflection of the waves at the zone boundary. So you've got one plane wave coming in at the zone boundary, and it's perfectly reflected off, and they add up to get you a standing wave. Okay, and the group velocity was 0. Okay, so that makes sense. Okay, let's just have a little look here. On the next slide, I'll also show this again, but here these wave functions have been plotted, okay, the magnitude of them squared. Here is the plus wave function here, which has it's proportional to cosine squared, as we'll see in the next slide. And the opposite one here is in the blue curve. Okay, and we know what the magnitude of the wave function squared is. It corresponds to your electron density. Okay? So these curves, the blue curve and the green curve, can be thought of as the electron density, or the probability of finding an electron at that position. So for example, if we're here at the origin and we are looking at the wave function, the positive wave function squared, it says that we will find a high electron density there. The other wave says, for example, if this is your atom, and this is your atom, in your lattice, it will predict that for the blue curve, there is a high electron density between your atoms, whereas the positive wave function predicts high electron density on the atom. I've got some new slides in here, but I will upload and write it over the one that's there already. This is the kind of similar thing that I sort of tried to explain there. And this is where I said the wave function squared is just proportional to the density, electron density. And so what I'm leading up to is now going to relate this kind of, in terms of the electron density to the band structure. Okay, so remember we have now, in the presence of this weak potential, a band gap here. What does that mean? It's a forbidden energy gap. It means that no electrons can occupy this space. Okay, no electrons, it's forbidden. Electrons can occupy here, and here, and here, and here. So at this point here, this was the plus wave function, and the plus wave function predicted presence of electron density at the position of an atom. I'm telling you this now because I'm leading up to some more slides. At this position here, at the same energy, okay, this predicts electron density between the atoms. What I want you to think about now is orbitals, s orbitals, p orbitals, okay? So this is a completely different way of looking at it, and I guess it's kind of leading up to the idea that we're going to do next of tight binding description. But we can think about, okay, here's a schematic of the wave function. This represents s electrons, big round, that's where their orbitals are. And these represent p electrons, okay? So if you have your atom here, you know what the p orbital looks like. It has no electron density has lobes going away from the atoms, so they're sketched here. And when we make the magnitude squared of the wave function, this is sketched here, okay? So all of this positive and negative will just go into positive. So what am I saying here? I think on the next slide it might be a little bit easier. Should get rid of that. Okay, so what you can think of is when you're here at gamma equals 0 in the very lowest band, you can think of this as being like s electron orbitals, okay? When you go up to here, and these are bonding, you think of this as bonding orbitals, s orbitals. When you go out to here, you can think of the band as having a character of s orbitals anti-bonding. And when you square that to get the electron probability, of course, you will predict electron density at the positions of the ion cores as well, okay, when you square it. Okay. Now, when we go, remember, we talked about wave functions here and wave functions here. At this point here, remember it predicted a high probability of electron density in between the ion cores, not on the ion cores. You can think of that as being like a P wave. So in one dimension, here's your position of your atom. Okay, atom here, atom here. This is like a bonding P state, okay, because you have overlap of the same sign of the neighboring orbitals. And when you square that to get the probability of electron density, you will get, you know, high probability here, high probability here when it's squared, okay? Now, the one up here, we haven't done it, but that has the characteristics also of P states, but anti-bonding. Okay, here you can see that these lobes have opposite signs. So this is like a P anti-bonding state here. So what I'm trying to relate now is how the wave function behaves at certain points in the band structure and how that can be related to atomic orbitals, I guess. Okay, there's one other aspect that we want to, I guess, understand is going back to the perturbation theory and the result that we get an opening of the band gap at the zone boundaries. It has a parabolic shape, okay, like this, and we want to see, try and understand why and how that comes about. So now this working is also done in your solid state Oxford Basics books. So I refer to that here. But what we're going to do is consider you are at a position not quite on the zone boundary, not exactly at pi on A, but just delta, a small distance away from it. Okay, so maybe here, maybe just away from the zone boundary. So then you're going to basically substitute that in for your K, and you are going to obtain an expression here that we'll go through together, I'll write it down, is proportional to that little delta squared, which gives you the little parabolic shape near the zone boundaries, okay? So if delta is squared here, and that's a distance in K space, that gives you the little parabolic curvature there. But what exactly has been done, so you don't have to bother going away and doing it. Let's do it here. Okay, so in the presence of no band gap, we have h bar squared k squared over 2m, okay? Just a free electron-like thing. And so what we are doing, it's okay, I thought it was a little bit blurred, but okay, we're going to just let k equal 2 pi over a delta, and k dash equal minus pi over a plus delta. Okay, looks like they are using n pi, so doing a general case. So just put an n pi in there. So then we get k squared is equal to n pi, putting it into there, over a plus delta all squared. N pi on a squared, just expanding that out. And then we just substitute it into 1, okay? So we end up with E0 n pi over a plus delta for the k equals to h bar squared on 2m n pi over a squared plus 2a pi delta over a plus delta squared. And then you can do the same for the other one, the k dash. Same thing here, n pi on a squared minus 2n pi delta over a plus delta squared. And with these two expressions, we substitute them into the secular equation. Okay, remember we had this one, E0 of k minus e of k plus g minus e minus v squared equals to 0. So basically what has been done is you substitute this in for that and this one in for that, okay? And yeah, just expand it all out with all of this stuff in and collect up your terms, and yeah, that's how the this expression is obtained, okay? So it's just a little bit of working, but you should end up with this expression. Now, what is this expression leading to? Firstly, it explains, as I mentioned before, this quadratic behavior because you've got your delta squared, but also it's introduced this kind of complicated term which can be called basically the effective mass. We've only done it in one dimension, so it's a bit of an unusual expression. And later on, I don't know if I'll get time this lecture, I don't know if in one of your assignments or quizzes you're going to be asked to derive the effective mass, so I'm going to go over a little bit of that shortly, or in the next lecture. So basically, I'll put this up now. This term, okay, you can see we have, you know, the normal electron mass there, right? So this term is going to be called, so lumping, say, this m together with this factor here, that's going to be called m star, which is your effective mass. And it's equal to this quantity here. Okay? So, as we'll see later on, the effective mass is not the real mass of the electron, but it's called the effective mass. It has the units of mass, but it's severely distorted due to the periodicity and the potential of the crystal. Okay, and later on we will see that the effective mass is inversely proportional to the curvature of your band structure. Okay, so I'm getting a bit ahead of myself. That's all I'll say about that for now. What's important here also is, you know, we had drawn just for the first Brillouin zone, or in the reduced zone, we had drawn like this, just this small part here. If you draw this in the extended zone, this is what it looks like. Okay, you know, so this dark one here corresponds to, you can see it has a free electron kind of shape, but it's nearly free electron in that it's got these, at the zone boundary, it's now got these forbidden bands, band gaps. And there's also one here, forms here, and so on and so on. Okay? So this is now has got, you know, contributions to the other G vectors in the reciprocal space. Okay? But as I said before, normally we just focus on the first Brillouin zone. And, okay, this is put here just to sort of, remember when we first started, we had this figure, and we started off with atomic orbitals. For example, here might be, at large separation, we might have two atoms, and they may have very well defined atomic levels, 3s and 3p. As you bring them together, here, the states overlap, and at the equilibrium lattice constant, you get two kinds of broad bands and a band gap. So here, in the free electron model, we're also getting a band gap. This is kind of leading to the approach of the tight binding, which we'll do next, where we start off from discrete atomic orbitals. Okay, I want to talk a little bit now about bands and how to occupy them. Okay, going back to that very first slide I had, for example, if we are given an electronic band structure and we are given what kind of material it is, can we predict, you know, where the Fermi level will be, where those bands will be filled up to? So the way we do that is with electron counting. So let's just go through this slowly. It's kind of important here. Remember that, okay, here's a band. The number of electronic states, or K values that it can have, is equal to the number of unit cells in your slab of crystal. Here, sort of, I don't know how many you've got, but those allowed K vectors or K values are indicated. So, if we've got n unit cells, we have n allowed states. And we can occupy those n states with two n electrons, spin up and spin down. Okay, two possible states per band. So that means if we have a material that's got two valence electrons in the unit cell, then we can easily occupy, or exactly occupy, fully one band, because that one band has two n possible states, and we've got two states for every unit cell, and we have n unit cells. We need states for two n electrons, and that's exactly what we have. Okay? If you have a material with an odd number of valence electrons per cell, then you will never be able to completely fill up a band, because you need 2n, so it has to be positive. So let's do an example. Even though aluminium is described as a nearly free electron-like material, you can see here it has a really free electron-like bands, and a little band gap here like we just had. Okay, so this is a real band structure calculated. Let's try and understand how that is metallic. Okay, so let's think about aluminium. We know it's FCC, not that that really matters for this problem. It has one atom per unit cell. Okay, so you know you've got one atom in every unit cell. And in this case, there are 3 electrons for every atom. Okay, so we've got 3 electrons in every unit cell. We've got n unit cells. So in one band, well, we need to find states for 3n electrons. Okay, but we know that one band can only hold 2n electrons. So 2n of those electrons go into the first band, and then the next band, which can also hold 2n electrons, we only need n more, so that's half filled. Okay? So aluminium has to be a metal in this simple electron counting method. Of course, this electron counting method doesn't always work, and we'll see one later, just shortly, that doesn't work. Okay, let's look at silicon semiconductor. Let's think about it. Okay, it has 2 atoms per unit cell in silicon, yeah. It's got 4 electrons per atom. So 2 atoms, 4 electrons. We have 8 electrons in our cell for every cell. So we need 8 times big N electron states for our 8n electrons. But we know each band can only hold 2n electrons, which means we can fill completely 4 bands. Okay? Here's the first band with 2n electrons. Second band has another 2n electrons. This here is a degenerate band, so there's 2 bands here. That can fill the other 4n electrons. And so that's perfectly filled, and so it can be a semiconductor. Okay? Doesn't have to be, but it can be. Another semiconductor is here, gallium arsenide. Okay, it's also got 8 electrons per cell. In this case, it has one of the atoms has 3 valence electrons. The other atom has 5, but still altogether it has 8 electrons per cell. So we need 8 times big N electronic states for these electrons to occupy. And so again, we have 8n divided by 2. We can fill exactly 4 bands. These have very similar band structure, actually. Okay. So, what about this material? This is beryllium. Beryllium has a hexagonal close packed structure. It has 2 atoms per cell, and each atom has 2 electrons. So we need 4 valence electrons per cell. And so we need altogether 4 times big N electronic states to occupy these 4 valence electrons per cell. And so you would think that you could completely occupy 2 bands, 2n in one band, 2n in the other band. And so you would think that this material could be an insulator if it wanted to be. In fact, it is got a band gap here. This part of the beryllium zone is exhibiting kind of a band gap and, semiconducting or insulating behavior. But clearly over here, it's metallic. Okay? So even if you have an even number of electrons per unit cell, it's not all that is necessary to be an insulator. Okay? Because this is kind of simple electron counting. It doesn't take into account the real material. But I think it's very important. It's an important sort of tool that gives you a first idea of how a material might behave and why it behaves that way. Okay. So switching topics a little bit, coming back to the effective mass, I'm going to just look at the actual expression for the real effective mass in 3 dimensions. Okay, switching ideas now. Now we want to apply an electric field. We're going to basically derive the expression for the effective mass of an electron in a particular material. Okay, so consider the change in energy, kinetic energy with time. Okay, here we're making a just a change here, chain rule, and we know that that is equal to. Let's see, this is the force, the electron charge times the electric field. And let's see here, we can rewrite, what am I doing here? Okay, so we're differentiating this with respect to V, half mv squared. You get the E dV is just equal to mv. So you're putting mv in there. And here you are keeping this, putting the m over there. So what we have got is the expression for dV dt equals to minus E over m times electric field. We're going to use that in the next slide. So we're just deriving a few parts of it here. So now we can consider, we remember those formulas from just before. We can now consider the kinetic energy change with time for a block electron here, the E dt. Okay, we had from before, that's equal to minus electron charge, electric field times the group velocity, v. And here in this case we have the energies h bar omega. So we get here dE decay, h bar outside of the omega decay. And this here is just the W decay, the omega decay is just the group velocity. So we get this expression here. And when you look at that, you can think of that as the equation of motion of an electron in k space. Okay? So this is just the force. Okay? E times the electric field. This final slide here is basically putting those equations together. We want to now, we have here the group velocity, which we've had from a couple of slides ago and earlier here. And we get the acceleration just by differentiating the group velocity with respect to time. Okay? And this is what we had from before. I said to remember it, decay dt. This is the equation of motion, if you like, in reciprocal space. And when it boils down, we can get then our expression for the acceleration of a block electron due to an electric field. So you can think of, okay, this is force, E times the electric field. If this is force, think of Newton's second law, F equals ma. Okay? So this coefficient here is like the inverse of the mass. Okay? So this expression here, when you turn this part of it upside down, take the reciprocal of it, you have got the effective mass. Okay, there's a constant here, h bar squared. What's the important point? The important point is that the effective mass, this is to the -1, but it's proportional to the inverse of the curvature of the energy versus K curve. Okay? So the more curved your band, the lower your effective mass is. Okay, so what does it mean here? We have lots of, each material has its own particular band structure. So if we are got this very simple situation here, if you have a band here that has a very low curvature, then this band will have a very large effective mass. And conversely, high curvature here means that the effective mass is low. Okay. And this is important for semiconductors mainly, and we'll get to that a bit later on, but want to introduce that concept just now. Okay, I'm going to leave it here for today, and on Monday we're going to look at the tight binding model as opposed to a nearly free electron model.